Hey guys, in this episode, we'll be learning about a super important basic lesson in chemistry Lewis structures. Now, what are Lewis structures? It's basically the representations for molecules that we commonly see all around the place. Like for methane, it would be like this. What else can we think of? Let's say we have HBr, so it would be like this, and HCl would be something like this. Now, how do we draw these? Let's go through it in a step-by-step process. So how do we draw these Lewis structures? What's a good way to do this? A good practice is to count all of the valence electrons in the molecule first. So let's say we have HCl. What do we do first? We count the valence electrons in its neutral state or its ground state. So for hydrogen, we only have one valence electron. For chlorine, we have 7. So that's a total of 8 valence electrons. Now, our second step should be counting the valence electrons when the octet rule is satisfied. So we know that hydrogen can only hold 2 electrons, meaning it cannot satisfy the octet rule, but rather it satisfies the duet rule, in which it can only hold 2 electrons max, so it already contains 2 electrons. So let's count the valence electrons when the duet rule and the octet rule are both satisfied. So in HCl, that would be 2 plus 8, which gives us a total of 10 valence electrons. And now our third step is to subtract these with one another. So that's 10 valence electrons minus the ground state valence electrons, which is 8 valence electrons. And then we divide that by 2, which gives us 2 valence electrons over 2, resulting in 1 bond. And yes, the result we get from this equation should be the number of bonds. So let's try to draw this. So H and Cl, 1 bond connecting them. And then we subtract that 1 bond, which is 2 electrons, to the ground state valence electrons. So it's 8 minus 2. We have 6 more electrons remaining. And these electrons will all go to chlorine since it can still hold them. 1, 2, 3, 4, 5, 6. And then 7 and 8, meaning these two are both satisfied by the duet rule and the octet rule. Let's have another example. Let's say we have CH4. So how do we know which atoms act as the terminal atoms and which ones act as the central atoms? So normally, our central atoms should be the least electronegative. With the exclusion of hydrogen. Meaning in this compound, our central atom should be carbon. Now let's find out how many bonds we should write down. So CH4 has 4 valence electrons from carbon, plus 1 times 4, since we have 4 hydrogen atoms, which gives us a total of 8 electrons. And then, if the octet rule and the duet rule are all satisfied, we should have 8 plus 2 times 4, so that's 16 valence electrons. And then we subtract these two with one another, so that's 16 minus 8 divided by 2, 8 over 2, this equals 4 bonds. And we draw 4 bonds around carbon. And that should already satisfy the octet rule for carbon, so there you go. And since we have 4 bonds, that's 8 electrons. We subtract that to the value of the valence electrons in the ground state. So it's 8 minus 8, that's 0. And once the number reaches 0, that means the structure should be complete and stable. So this is a correct way to draw the Lewis structure of CH4, also known as methane. So let's try to apply what we've learned here. Let's have some practice real quick. So CH3, CH3. How can we draw this in its Lewis structure? We know that hydrogen is an exception for the central atoms, and carbon should be at the center. So both of these should act as the central atoms. But first, let's count the valence electrons. Carbon and carbon, that's 4 times 2. There's 6 hydrogens, so that's 1 times 6. So that's 6 plus 8, which is 14 valence electrons. And then we have 8 times 2 plus 2 times 6. That's 16 plus 12, which is 28 valence electrons. Now we subtract 28 by 14 divided by 2. It's going to be 14 divided by 2, 7. I have 7 bonds. Let's just lay them out like this first. So 1 bond, 2 bonds, 3 bonds, 4 bonds, 5 bonds, 6 bonds, and 7 bonds. And let's see if this is complete and stable. So 7 times 2, since every bond is 2 electrons, that's 14. So subtract that to the ground state value, we have 0. Meaning that this is a complete and stable representation of the Lewis dot structure of CH3, CH3. Let's have another problem. CH5N. How do we draw this? Which atom is less electronegative? So we know that electronegativity goes down the more left you get on the periodic table. And in our first row, we have B, C, N, O, F, and E. Meaning the less electronegative atom should be carbon. So we draw it like this. C, H, H, H. But then, if we don't connect nitrogen, we can't have the full structure bonded properly. So we have to connect carbon to nitrogen. And we're missing 2 more hydrogens. So we write them here. Now, what is the ground state valence electrons? So we have 4 plus 1 times 5 plus 5. So that's 14. And then that's 8 times 2 plus 2 times 5. So that's going to be 16 plus 10, which is 26. 26 minus 14 over 2 is going to be 12 over 2, which is 6 bonds. Let's see if that's true. 1, 2, 3, 4, 5, and 6. That's it. We got the 6 bonds. Now, is this a complete and stable representation of the structure? No. Nitrogen has yet to be satisfied with the octet rule. So let's subtract the number of bonds we used to the ground state electrons. So 6 times 2, that would be 12. We have 2 electrons remaining. Now, what do we do with 2 electrons? Yep, we make a lone pair. So 1, 2. And that's it. Subtract the lone pair that you added, you get 0. Now this is a complete and stable representation of CH5N. Let's try out a problem that involves multiple bonds. So let's use H2CO. And the Lewis structure is already pre-written for us. We just need to know where to connect the bonds and how many bonds to put. Now, we know that hydrogen can only hold one bond each, so let's immediately connect that. And now, we have to make sure that the octet rule is satisfied for carbon. So how many bonds do we have to apply to one more atom to have a full octet? That's right, a double bond. We need two bonds. So 1, 2. But we can see that oxygen doesn't have a full octet. So what do? That's right, we add lone pairs. So 1, 2, 3, 4. So this should be your acceptable Lewis structure for H2CO. And that's pretty much it for multiple bonds. You can also rewrite it like this, in its proper geometric shape. But we'll get to that in a different lesson. Now let's move on to a different concept. Formal charges. Now, what are formal charges? Formal charges are basically things that we have to check to see if the electrons are properly distributed in a molecule, to determine if there would be an overall charge for the molecule or not. So basically, if there's a formal charge, the whole molecule could become an ion. Now, how do we find the formal charge? The easiest way to do this is to count the number of valence electrons and then subtract it to the number of lines or bonds plus dots or electron pairs, rather lone pairs, around the atom. So let me show you how to apply this. Let's say we have this structure. These brackets are here basically to denote that the whole molecule contains a charge. So how you would write this is basically NH4 with a plus sign. That's what it means. Now, let's find the formal charge of the nitrogen. So, what is nitrogen's valence electrons? Nitrogen has 5 valence electrons, so it's 5. Then we count how many lines are around it. 1, 2, 3, 4. So it's 5 minus 4. No lone pairs in sight, meaning our formal charge should be plus 1. Let's do another example. Let's have CH3, N, triple bonded to C. So let's expand this more. Now, what is the formal charge of C, N, and C? Let's do the carbon on the left first. So that's 4 bonds connected to carbon, meaning 4 lines, and carbon has 4 valence electrons, so it's 4 minus 4 equals 0. Carbon has an overall formal charge of 0, the left carbon. Now let's find out what the formal charge of the nitrogen is. So that's 5 minus 4 lines is equal to plus 1. So we have a charge of plus 1 for the nitrogen. Now let's find out what the formal charge of the carbon on the right is. So how many dots do we see? 2. And we have 3 lines. So that's carbon is 4 minus 1, 2, 1, 2, 3, 4, 5. So that's minus 5. Our charge for that is negative 1. And that's it. It's basically how you find the formal charge. Quite simple. And let's try out these problems. Now, let's say we have an ion, CH3O minus. Now, how would you draw that? as I stated earlier, we're going to need brackets because there's a charge. And should look something like this. There we go. Let's just try to find out the formal charge of carbon and oxygen here. So for carbon, that's immediately 0 because there's 4 bonds around it and it has four valence electrons. Now for oxygen has 6 valence electrons, and let's count everything around it. 1, 2, 3, 4, 5, 6, 7. So we have 7 stuff around it, meaning 6 minus 7, that's -1. Hence, where this charge came from. And in our previous example, there was a +1 charge and a -1 charge, which is why there's really no brackets to denote that, as the charge really cancels out anyway. Now, for the next example, we have Hc2 minus, which we can just write it like this. Now, what is the formal charge of each of the carbon atoms? This one is 0 immediately off the bat, and this has 2 dots and 3 lines. So that's 5. 4 minus 5 is -1. Hence our formal charge, or rather the charge of the ion, which is negative. And that's it. That's all you have to know about formal charges. So let's apply that to these last few questions. Now, what is the formal charge on the O atom in each of the following species that contains a multiple bond to O? For this, we have 2 dots and 3 lines around it. So that's 1, 2, 3, 4, 5. That's 6 minus 5. So that's a +1 charge. For this, that's 1 line, 2 lines, 3 lines, 2 dots. So it's 5. Another 6 minus 5. It's going to be +1 again. And lastly, 1, 2, 3, 4, 5, 6. That's 2 lines plus 4 dots. It's going to be 6 minus 6, which means the formal charge is 0. And that's it. That's all you guys have to know about Lewis structures and formal charges. I hope you learned something. Please leave a like, share, and subscribe. And stay tuned for upcoming chemistry videos. Thank you for watching.